In this lesson, we're ready to start turning the page to the next chapter in our understanding of physics. Up to this point, we've been studying kinematics, which is motion. In this lesson, we're still going to be studying motion, but we're going to be studying it from another perspective, the perspective of dynamics. In kinematics, we just took for granted that some objects were accelerating and some objects were moving at constant speed. Some objects were not moving at all. But we didn't really explain why some objects accelerate and some do not. In this lesson, we're going to start developing tools to understand what causes acceleration, or what causes some objects to move at a constant speed, or what causes some objects to not move at all. In order to develop this understanding, we need to understand Newton's 3 laws of motion. And in this series of lessons, we're going to cover Newton's first, second, and third law. We're going to start today with Newton's first law of motion. As we get started, it's just important to distinguish between kinematics and dynamics. So when you compare the two definitions, there's one clear difference. Kinematics is the study of motion without considering forces, and that means we're not considering what's causing acceleration. We're just taking acceleration at face value in problems. We're told there's an acceleration, and then we can calculate things based on that given acceleration. Well, in dynamics, we're studying how motion results from combinations of forces, and really we're understanding how forces cause objects to accelerate. Or sometimes forces don't cause objects to accelerate, and we can predict how those objects are going to move when the forces are either balanced, there's no acceleration, or unbalanced and there is acceleration. And that's what dynamics is all about. And that's what we're going to be learning in this unit. Now, you may be wondering what a force is, because I really just introduced that topic. I've probably used the word force because it's hard to talk about kinematics even without ever talking about force. I'm sure I've called gravity a force a couple of times. But now let's develop a formal definition of what a force is. And in this lesson, I'm just going to give you the verbal definition. When we talk about Newton's second law, I'm going to give you a mathematical definition of a force. But the simple way to envision what a force is it's simply a push or a pull, and it's capable of doing something. It has the potential to cause acceleration. Forces are what can cause acceleration. Now, they don't always cause acceleration. We'll talk about a situation where we can have balanced forces that don't cause any acceleration, but forces all have the potential to potentially cause acceleration to happen. And what are we accelerating? We're accelerating an object that has mass. Also, it's important to note that forces are expressed as vectors. And all that means is a force has a magnitude and a direction. We'll talk much more about the magnitude and how we measure forces again when we get to the mathematical treatment in Newton's second law. For now, it's important for you to be able to picture a force as a push or a pull in a certain direction, and direction is important. Okay, so let's consider. Here we have a crate. In a lot of our sample problems and sample investigations involving forces, we're going to consider this generic object. This is a crate that we can slide along a surface. Okay, now notice I'm not using a wheel. If I used a wheel, there would be other kinds of motion involved. Wheels rotate. Crates just simply slide along surfaces. And we're going to be using this example a lot in future problems because this is like the most basic example of something that follows the rules of dynamics without bringing in a bunch of other physics to explain it as well. Now, if we have a crate, an object, that crate is going to have a certain amount of mass. And that's important to realize too. We're dealing with accelerating objects, and all objects are made up of matter, so these objects that we're accelerating have mass. Forces are always acting on masses. All right, now, here we have a person pushing a crate. I'm going to call this person A and person B pulling the crate. All forces have to be caused by agents. Something is causing that force to apply itself to the object. In this case, my agents are obvious. It's going to be person A as one agent and person B applying the force to the crate. Also, most of the time, the agents causing the forces are doing so because they are actually making contact with the object. We call those contact forces, where the agent actually has to touch the object to apply force to it. Most forces are contact forces. However, there are a few non-contact forces that we'll talk about a little bit later in this lesson. So notice what's happening. Person A is putting hands on the crate and applying a push force to the crate. Person B is a second agent putting hands on the crate and applying a contact force, pulling the crate with a forward force. So both of the forces are in the same direction. One's a push, one's a pull. What's the difference when we talk about a push and a pull? Well, a push is always directed away from the agent. You see how it's directed away from person A? A pull force is directed toward the agent. In this case, the pull is directed toward person B. Okay, so that's important to realize when we talk about pushing and pulling. We're talking about similar activities, applying forces, but they're in different directions with respect to the agents. However, they can be in the same direction with respect to each other. The reason that this happens is because notice my agents are on opposite sides of the crate. So in order for them to have the same direction of force, one has to be pushing and one has to be pulling. Now, this is not a very effective way of modeling forces. It's helpful to draw a picture of what's happening, but when I get into the mathematical part of actually analyzing the forces, there is a typical standard type of diagram that's used in physics to show all of the forces acting on an object at the same time. And it's called a free body diagram, and it's important that you get good at drawing these free body diagrams. Here's how free body diagrams work. So the first thing I'm going to do with a free body diagram is draw the mass as a dot at the center, the mass on which the forces are acting, and there can only ever be one in a single free body diagram. I have to choose the object that my free body diagram is going to focus on. And if I have multiple objects that are moving in a problem, or multiple parts of the same object that are moving, and I have to analyze them individually, I can only draw one free body diagram at a time, either assuming the whole moving system is one object, or each part of the system is its own object. In this case, it's easy. I have one mass on which the forces are being applied, and that is the crate. I'm going to represent it with a dot. The next thing we're going to do is draw and label all of the forces originating at the dot. Now, I didn't give you enough information about this crate problem to show you what all of the forces are going to be acting on the crate. What I'm going to do is I'm going to share with you what I know would be some forces that are acting on the crate. If you're lost a little bit in identifying these forces, don't panic. I'm not expecting you to be able to memorize what all of these forces is right now, and we're going to talk about each one individually in a future lesson. But I am going to share with you what the forces would be in this situation. So obviously we have the two forces that are already pictured. We have the force of agent A and the force of agent B pushing and pulling the crate, and both of those forces are acting in the same direction. So I'm just going to draw both of those. I'm going to draw them slightly off center on the center dot so that you can see them both. Both of them should be coming out of the dot. Now, what you could also do is you could also do a little vector addition if you were drawing this on paper to show that these are being added to each other toward the right. So I would draw the vector for force A, and then immediately starting at the end of the vector for force A, I could start the vector for force B. That's also an effective way to show two vectors that are overlapping one another. Otherwise, if I just drew an arrow and then another arrow directly over the top, you wouldn't be able to see both of them. What other forces are acting on this crate? Well, I know that this crate is being either slid across a floor or it's stationary on a floor, and these two agents are trying to slide the crate, but it's possible that the crate is just so massive that they're not able to move it. Why would that be? Why would there be something resisting the motion of the crate along the floor? Well, there's a force that resists motion when you slide objects across the floor, and that force is called the force of friction. We're going to learn that if the crate started at rest and these movers are trying to push this crate forward, but the force of friction is great enough to match the force that they're putting on it when it starts at rest, they won't be able to move the crate forward. We're also going to learn that if the movers are pushing the crate forward, it's possible that there's still friction force, but they're able to move the crate forward. And we're also going to learn that it's possible for them to accelerate the crate forward depending on the friction force as well. So friction force is another important force acting on this crate. Another force acting on the crate, well, we talked a lot about gravity in the previous unit, and we talked about gravity accelerating objects. Gravity is also a force, and it's important to visualize gravity as a force capable of accelerating masses. Gravity is pulling downward on this crate, pulling it toward the earth. And then another force that's acting on this crate is one that you're probably not familiar with. It's known as the normal force, and it's the force that a surface will push back on an object with to resist gravity. Normal force is the reason you're not falling downward into the floor right now, because gravity is tugging at you. Gravity wants to pull you downward toward the center of the earth. Normal forces exist whenever a surface pushes back against gravity directed in the opposite direction to resist the downward pull of gravity. And these are all the forces that would be acting on this crate. I've drawn a free body diagram now to represent all of these forces. And again, you're not required to walk into a problem at this point and be able to identify all of these forces, but just so you know, these are common forces that you're going to see across a wide range of problems that we're going to be working in physics. Friction force, gravity force, normal force. It's going to eventually be important for you to recognize when these forces are acting and in what kinds of problems they are not acting. All right, the last thing we need to do is identify the agent and the object of each force. Now, technically, this isn't part of the free body diagram, but it is an important part of analyzing your free body diagram to understand what's happening in your problem. So what are the agents and objects of each of our forces? Well, all right, let's look at F sub A. Our force A is the force of person A on the crate. The agent is person A, the crate is the object. Same for B, right? It's just the same thing except it's being pulled instead of pushed. It is in the same direction though as force A. What about these other ones? What about the force of friction? Well, the force of friction is the force applied by the surface across which the crate is sliding to the crate, the surface on the crate. So the surface on which something slides can be the agent of a force that's being applied. It's actually a very common agent of a force that's being applied. The normal force is the force that the floor exerts on the crate. Now, so far, all of these agents are actually touching the crate, and therefore all of these would be labeled as contact forces because there has to be physical contact for these to act. What about gravity, though? Gravity is the force of the center of the earth on the crate. Gravity is a very, very common non-contact force. If we were to drop this crate from above the earth, the force of gravity would still be acting on it without having to touch it. So gravity is sort of a unique force in that in common problems that we're going to be working in physics, gravity is a very common non-contact force. Other non-contact forces would include things like magnetic forces and electromagnetic forces. But for right now, we're going to just focus in on gravity because that's a much more common one for the types of problems we're going to be working in physics. Now notice that all of the objects of these forces are the crate. They're all working on the crate. That's excellent because we want our free body diagram to show all of the forces that are actually acting on the object pictured in the free body diagram. If we have another object listed here, it's possible that we have a force that's acting on something other than the crate, and we maybe need to eliminate that force from our free body diagram as we model what's actually happening here. All right, now the next step after we've done these steps is to actually do some vector addition. And why is that? Well, we can add the forces in a free body diagram, and it tells us something important about what those forces are doing. We call that sum of the forces the net force. And it's just the resultant vector sum of all of the forces that are acting on an object. Mathematically, we represent that with this equation. The sum of the forces, we use the Greek letter sigma, and notice that I'm talking about vector forces using the vector notation above the F in F net. So the sum of the vectors of the forces is equal to adding just force 1 plus force 2 plus force 3. And I've got all of these forces in this list in my free body diagram. So I've shown everything that's acting here in the free body diagram already. Now I just need to add those together. So in this particular case, for this particular problem, the sum of the forces equation looks like this. Fa plus Fb plus the friction force plus the normal force plus the force of gravity. And when I add all of these forces together, I will get my net force, the overall force that's actually acting on my object. Well, let's see what happens when I do vector addition with these forces. So to do this, and normally if I were doing this on paper, I would draw a separate diagram showing the forces added together. I'm moving away from my free body diagram now to a vector addition problem. They are two separate things. Free body diagram is the first thing I draw, and now that I have all my forces, I'm going to do vector addition separately. In my slide here, I have the benefit of just being able to move things around. So I'm just going to move these forces around to show you how vector addition would actually work. I'm going to slide my force of gravity over, my two push and pull forces down to the bottom there, and then my normal force. Now, I could add these forces together in any order, and I would end up with the same resultant because vector addition is commutative. It doesn't matter which forces I draw first or how I add these together. This is just the convenient way for me to add them on screen here. And you see that when I add all of these vectors together, it brings me right back to the origin. That means that my resultant is 0. So all of these forces balance each other out. Here's what Newton's first law of motion says, by the way, about what the net force tells you. So Newton's first law of motion states something that's actually pretty counterintuitive. The first thing, though, makes sense. An object at rest remains at rest. You're used to seeing that happen in real life. Unless you do something to an object that's just sitting there, it's going to remain just sitting there. It's not going to do anything on its own. An object at rest remains at rest. Here's the part that gets to be a little bit tricky to picture because your brain is not used to thinking of things this way. A moving object continues to move in a straight line at a constant speed all on its own. So what this is saying is that if your car is coasting down the road, your car's natural tendency is not to come back to rest. It's to continue moving in a straight line at a constant speed. But your experience tells you that if you're in a car and you don't hit the gas pedal, the car will eventually slow down and slow down and slow down and come to rest. If you're on a skateboard or rollerblades moving forward, and you just coast, you just roll forward without pushing off the ground at all, eventually your experience tells you that you're going to roll more slowly, more slowly, more slowly, and then eventually slow down enough to come to rest. So how could it be that an object that's moving is supposed to keep moving in a straight line at a constant speed? Well, here's the other part of Newton's first law of motion. Unless the object is acted on by an external net force. So objects will move at a constant speed, or I guess stay at rest as well, if there is no external net force acting on the object. The reason this is counterintuitive is because most people aren't really used to considering friction, which resists forward motion, as a force. You picture your own pushes and pulls as forces very easily. But you don't really picture friction resisting motion as a force. However, friction is a real force that is in the real world and commonly acting all the time. So if you are in a car that's coasting or on a skateboard that's rolling or rollerblades, friction is going to be opposing your forward motion, exerting a net backward force, and causing you to have a negative acceleration. In fact, the only way to overcome friction is to apply your own forward force, the opposite direction of friction, so that you don't have an external net force. You're applying a forward force that cancels out the force of friction to keep yourself moving forward at a constant speed. Okay, so what's happening with our people pushing this crate if there's no net force? Does that mean that the crate is just sitting there and not moving? Well, because there's no net force, all of our forces add up to 0. It means that the crate is at rest, or the crate might be moving at a constant speed. We actually don't have enough information in this problem to determine if the crate is moving. What we do know is that the crate is not accelerating. When all of the forces are balanced, the object is either going to move at a constant speed or stay at rest. There can't be an acceleration. And again, we get to Newton's second law of motion. We're going to see why it is that an object will not accelerate if the net force is 0. By the way, we call this situation where there is no net force when we add all of the forces on an object together and the resulting net force is 0. We call that equilibrium. So right now, this picture that we're looking at of these two people pushing this crate, and there's friction involved and gravity and normal force, this is a system that is at equilibrium, and there's going to be no acceleration. Either the crate is at rest or it's moving at a constant speed. And looking at how hard these two people in this picture are working, I like to picture that the crate is sliding forward at a constant speed. These people are putting in a force constantly. They're putting in a force to move the crate forward, but they're not accelerating it forward. They're just putting in enough force to overcome the force of friction, which is pushing the crate backward, and it's ending up sliding forward at a constant speed as a result. Okay, so that's the first key realization, and I hope that I've driven that in. It's important to realize that if there is no net force, the net force is 0, it doesn't necessarily mean an object isn't moving. It just means that an object isn't accelerating. Remember, forces predict acceleration. They help us to explain why objects accelerate or don't accelerate. And in this case, if the forces are balanced, there's no acceleration. Let's take a look at another example. This example is a little more complicated. And that's the example of a car driving forward on the road. Do you realize that the thing that causes a car to drive forward on the road is actually a forward version of a friction force? Now, at first glance, this doesn't make sense because we were just picturing a crate that was sliding across the floor, and the crate that was sliding across the floor had a friction force resisting forward motion. But think about what's different about a car. A car has wheels, and those wheels have traction, and that traction is caused by friction between the wheel and the road, and the wheel actually spins backwards where it contacts the road. And because it's spinning backwards where it contacts the road, the friction force is opposing that backwards direction motion. The friction force is pushing forward, propelling the car forward. And again, if this doesn't make sense to you immediately, this is a situation we'll be considering again in the future. But just keep in mind that you do this as you walk across the floor too. You push your foot against the floor and you push backward with your foot. There's a friction force opposing that backward motion that pushes you forward. And that's how you move. If you were trying to do that same thing on a perfectly frictionless icy surface, you wouldn't be able to walk because you couldn't push backwards against the frictionless surface. But this force of friction isn't the only force that's acting on a car. This is the forward propelling force, the important force that cars are designed to provide. But there's a bunch of other forces too. There's the air resistance force resisting the motion of the car forward. There's a rolling resistance force that's caused by the way the wheel deforms against the ground. Rubber tires aren't going to remain completely rigid. They're going to deform a little bit against the ground, and that's going to oppose the motion of the car. There's also that gravity force. The center of the earth is trying to pull this car downward, and you could probably imagine what the final force I'm going to list is going to be: the normal force of the road on the car preventing it from falling downward because of gravity. The surface below the car is pushing back up on it. All right, now let's see if all of these are valid forces. The force of friction is the force of the surface, that's the agent causing the force, on the wheels of the car. That's the object. The air is the force of the air on the car. That actually is pretty straightforward. The rolling resistance is the force of the road on the tires of the car. The normal force is the road pushing up, again, on the tires of the car, but we would just say it's pushing the entire car at the same time. And then the force of gravity is that non-contact force, the center of the earth pulling downward on the car. Again, all of these are contact forces except for gravity. And all of these are valid forces, although when you look at this, notice that I've changed what my object is at times. Instead of just saying car for everything, I said wheels and tires. So here's what you have to ask yourself. Are the wheels and the tires a part of the car such that when I do my next step and start writing my free body diagram, that dot that I make would also include the wheels and the tires of the car as a part of the object. And yes, I think it's not too far stretched to say, obviously, even though they move independently of the body of the car, we could say that the wheels and the tires are part of a car. So we're just going to include those in our object that all of our forces are acting on. I'm going to show you why that was important later. There's an important reason we made that consideration. For right now, it's enough to note that we are just picturing the entire car within this dot. And then let's make our free body diagram. We're going to show all the forces coming out of this dot in the direction that they're actually moving. So here's my friction force, my air resistance force, my rolling resistance force, and then I'm also going to have a gravity force pulling downward and a normal force pushing upward. Here's my free body diagram. I pictured all of the forces that are acting on this car. All right, the next step is going to be to do a vector addition problem separately from my free body diagram. This is not vector addition, this is just a picture of all of the forces as a part of a model. So I'm going to start vector addition, and remember, it doesn't really matter which order I add these in. As long as I'm using the correct technique for adding vectors, vector addition is commutative. So I'm just going to start by putting my center point and then my normal force and my gravitation force. And notice what happens with these two forces. The normal force points up a certain amount with a certain magnitude. The gravitation force is downward, and they have the same magnitude as each other. So notice that when I add these two, it takes me back to the spot where I started. These two forces are going to cancel each other out. I'm not going to have a net vertical force because the weight, the gravity force pulling downward perfectly cancels out the normal force going upward. Next, I'm going to add my friction force, which in this case was a forward force that's propelling the car forward. That's that traction force. And then I'm going to put in my air resistance and my rolling resistance. And notice that I do have a resultant here once my forces are all added together. So I'm just going to get rid of those forces that cancel out. And you can see the resultant is going to start at the tail of the first and go to the head of the last. It's going to start right at the beginning of my friction force, and it's going to head in the same direction as my friction force, but it's going to fall a little bit short because the air resistance force and the rolling resistance forces dissipate the forward force, the traction force of the car. So my net force is going to be a net force pointing forward. And what do we know if there's a forward net force? Well, that means that the mass of the car has to be accelerating forward. And it's going to always accelerate in the direction of force. And that makes sense. This is the direction along the roadway that means that my car's engine must be turning the wheels in such a way that they're able to produce a traction force against the road that's going to accelerate the car forward. And by the way, once you get going at a faster speed, keep in mind the air resistance force is going to increase. The rolling resistance force may increase as well, depending on what all goes into that force. So as a result, eventually, as I speed up, my forces will balance out and I will no longer be accelerating forward. But for right now, I'm accelerating forward at this moment in time. All right, so at this point, we've talked about almost all of the parts of Newton's first law of motion. We talked about how an object at rest remains at rest, or an object that's moving continues moving at a constant speed and in a straight line unless there's an external net force. So the problem with the crate, those movers pushing that crate, were moving it at a constant speed or not moving it at all because there was no net force. Then we talked about the problem with the car moving forward, which had a net forward force. So that means that the car was accelerating in the direction of the net force. But what we haven't really talked about is that word external, unless acted on by an external net force. Well, what does that mean? That's going to be an important thing to consider as well. So if we consider our car again, I'm just going to make the car a little bit larger. A car has very many moving parts, all right? And the wheels are going to be moving independently of the engine, which is also moving, and then the whole chassis of the car is moving along with it, but the chassis is pretty much remaining fixed with respect to the wheels, which are remaining in a fixed position with respect to the engine. You know, the car's not blowing apart all over the place. We treated this object that's actually a system of moving pieces as just an individual object for the purposes of our force problem and our free body diagram. We just called that dot the entire car, all parts of it, even though some parts were moving independently of each other. And that's what we have to do with free body diagrams. They're a model and a simplification, and we have to make a free body diagram for each object we are considering in our problem. If I considered the wheels separate from the rest of the car, I would need to consider free body diagrams for the wheels and for the car, and that would make this problem much, much more complicated to work. So let's consider one specific wheel of the car, and let's consider a force that maybe seems to exist, but I didn't include it in my list. So as this wheel spins, notice we had that spinning motion around the outside. This is what allowed for that traction friction force at the bottom to push the car forward. As the wheel spins around the outside, it has to be spinning on something, okay? It's either spinning on like wheel bearings or it's spinning against the transmission. And whatever it's spinning against also has to have a resistive force, right? Like we can grease up wheel bearings the best that we can. And wheel bearings are just a circular object that allows the wheels to spin on them. And we grease them up to make them as low friction as possible, but there's always going to be at least a little bit of resistance to spinning caused by wheel bearings or caused by the transmission or caused by different parts of the car. So why didn't we include the force of the wheel bearings? After all, I could identify an agent and an object. The force of the bearings is the force of the bearings maybe on the axle would be a good way to say this. The wheel bearings that are moving around, allowing the car's wheels to spin, but there's rubbing going on between the parts of the bearings and the axle. Well, we'll say that that's what's happening there. So why didn't I include that force in this drawing? You may remember that earlier in an earlier video we talked about the object model versus a system model. And an object model applies when the system is essentially rigid, which means we don't have to consider the individual parts of the system. We just assume it all moves together with the same motion. A car is pretty much semi-rigid. Like the wheels aren't moving at a different rate from the engine, at a different rate from the body of the car. Otherwise, they would all be flying apart from each other. They're all pretty much moving together. So we can consider a car to be an object, as opposed to a system, when the internal movement of the system matters and we need to analyze all the points that are moving with different motion. In other words, we would need separate free body diagrams for each of the parts. We're considering the car to be an object, and that means that all parts of the car have to be part of the object. Internal forces occur when forces are exerted from one part of the system to another part, exerted on one part of the system by another part of the same system. And internal forces don't actually contribute to the net force, because if all of the forces are internal, then parts of the system maybe will accelerate with respect to other parts of the system, but the actual system doesn't accelerate based on those internal forces. So does that make sense? Within a system, you might have individual accelerations of different parts, but the center of mass of your system, if you're treating the system like an object like we are here, we're just considering the center of mass. The center of mass doesn't accelerate because of those internal forces. Now let's go back to the force of the bearings on the axle. Are the bearings a part of the car? Yes. Is the axle a part of the car? Yes. And that makes the force of the bearings an internal force. And therefore, we don't consider it when we consider the external forces, like the earth on the car, the road on the car, the air on the car. All of these are things that are external to our object, the car, so they do result in external forces. But the bearings on the car would be an internal force, and therefore we would not consider it with our external forces. Lastly, the center of mass of a system, even if there's internal forces, the center of mass of a system is always going to accelerate in the direction of the net external force. So even if you have a complex system with things moving within the system, and we're just treating that system as an object for the purposes of a force problem in our models, if we're treating that system like an object, the center of mass of that system, wherever the mass is located between all of the masses that are in our system, the center of mass is what's going to be affected by the net external force, and that's what's going to accelerate in the direction of the net external force. All right, this is a heavy lesson, and it feels like we covered a lot of ground, but we're going to be coming back, circling back to a lot of these concepts as we learn about Newton's second and third law, and hopefully you have a better understanding of what dynamics is and how Newton's first law applies.